presentation is about a powerful method to recognize patterns in data for diagnosis, prediction, and decision support. It's simple and useful for decision support in the real world, and I believe could be equally helpful in modeling and simulation. But first, I'd like to tell you a short story. Many of us wear a health monitoring device. These use sensors to measure steps walked, exercise intensity, sleep quality, etc. But some of these device makers are being sued by their customers for inaccurate pattern recognition. This slide shows an example of the problem. The upper graph shows me walking 10 steps, but when I play guitar as shown in the lower graph, I have to take the device off my wrist because it can't tell the difference between me walking and strumming the guitar. Several people have told me that they have the same problem when on a riding lawnmower, a Harley motorcycle, or pushing a shopping cart over a rough parking lot. Failing to keep your promises can be bad for business. Living creatures are marvels of pattern recognition. Some examples shown here include the dog Nipper in the painting his master's voice, being able to identify your car in a crowded parking lot with just a glimpse of a fender, trained FBI agents easily spotting counterfeit money, disease diagnosis by healthcare professionals, and recognition of faces from a very early age. So who is Mahalanobis Taguchi? Dr. Mahalanobis was the founder of the India Statistical Institute and invented a new method for numerical pattern recognition in the 1930s called Mahalanobis distance. Although innovative, it wasn't very useful without desktop computers to handle the required matrix math. In the 1990s, Dr. Taguchi, developer of Taguchi methods, helped Dr. Mahalanobis to incorporate optimization and prediction into the approach. Using readily available desktop computing, they were now able to deploy what is now known as the Mahalanobis Taguchi system, or MTS. So let's use a simple example to learn about MTS, evaluating an individual's height and weight. If the blue bell curves on this slide represent the height and weight of everyone on planet Earth, we could ask if an individual is where they ought to be. Tables of recommended height and weight are readily available from the doctor's office. If graphed, those tables might look like this. Data points inside the red oval represent healthy or normal conditions of height and weight. Each new individual can then be easily evaluated as healthy or not healthy. That's because the graph has provided us with two important things. First, we have a reference point from which to measure, the center of the healthy space in the red oval. And second, a measurement scale defined as the number of healthy space diameters away from the center, with 1.0 or less being healthy. An individual's health is then evaluated as the number of healthy space diameters they are from the center of the healthy group. It looks like about 1.75 for me. Now, let's learn about the MTS process using a more complex example with 4 parameters instead of just 2. In this example, we'll go quickly through the 4 steps of MTS as shown here. For our complicated example, we'll use gender, height, waist, and waist size to generate a normal space, confirm the discriminating power of our new measurement system, identify critical parameters, and optimize and implement the optimized measurement system. In task 1, we define the normal or healthy space by selecting representatives to include in that healthy group. Then we normalize the 4 dimensions of height, weight, gender, and waist size. Third, we create a correlation matrix of the 4 dimensions. Then we calculate the inverse of the correlation matrix. Although this sounds complicated, both steps are easy in most analysis software. Finally, we calculate Mahalanobis distance for each healthy individual by putting all these values into the formula for Mahalanobis distance as shown. Note that the group average for the healthy group is near 1.0 as a result of the earlier normalization step. What this gives us is a normal or reference space against which we can compare new individuals. You can think of it as a bubble with a center defined in 4 dimensions and a unit diameter of 1.0. Let's look at the results of creating this normal or healthy space for our 4-dimensional problem. Now we can plot our results in just 2 dimensions on a simple bar graph, no matter how many parameters are included in our recognition system, dozens or even hundreds. The healthy reference space appears as the brown dashed line at an average Mahalanobis distance of 1.0. We can now evaluate new individuals using their distances from the center of the reference space. The lower the Mahalanobis distance, the closer an individual comes to matching the reference group. In task 2, we confirm the discriminating power of our new measurement system. We select individuals across the range of expected possibilities, like 12 of my workmates shown here. We calculate Mahalanobis distances for each one of these 12, then confirm that our new measurement system correctly evaluates individuals relative to each other and to the normal reference space. Next, we determine which parameters to keep or eliminate using Dr. Taguchi's design of experiments methods for optimization. The Mahalanobis distances are each recalculated under two conditions: use or don't use, each of height, weight, gender, and waist size, and effects on sensitivity are evaluated. We see that sensitivity is greatly improved by eliminating height from our analysis, as shown by the blue bars in the bar chart. Not only is sensitivity improved, but we decrease the amount of data that we must process and store. One last slide in our effort to answer the all-important question, does this data make me look fat? This slide shows the Mahalanobis distances calculated across a range of typical body dimensions. Perhaps you can find values in the table that are close to your own to see how you compare to the healthy group defined by the medical profession. Dr. Shuichi Teshima is the leading authority in MTS today. This flowchart from his latest book shows the MTS analysis process for all 7 possible situations. The green highlighting is what we covered in our body dimension example. In all cases, the math is similar and straightforward vector analysis. A bachelor's degree engineer with an Excel spreadsheet can do it, which is one of the advantages of the MTS method. Here's a brief comparison of several popular pattern recognition methods like PCA and neural networks to MTS. MTS provides consistent advantages, particularly in its capability to reduce the size of data sets required, its ability to separate normal from abnormal individuals, and its data analytic approach instead of statistical analysis. Now let's look briefly at a few examples where pattern recognition is needed and MTS is being applied. One of my recent clients provides software to monitor health of power plants and machinery. They want to move beyond just reporting pressures and temperatures to accurately predicting future failure. Candidate selection is an innovative application of MTS. Here's an early version of an IT company's employment survey. For the highlighted questions on the slide, can you guess whether to use or don't use? MTS Analysis told this company that they would make better candidate selections if they use appearance, don't use the karaoke question, don't use the comics question, use draw or paint, use shirt buttoning, use gender, but don't use age. MTS pattern recognition has improved results in hiring, loan application, college admissions, and performance evaluations for promotion of employees. MTS pattern recognition is also being used for maintenance planning for some complex machine tools. Many liquid food products are packaged in cardboard containers using complex equipment. Downtime for maintenance, like cutting head replacement, is costly, and operators want to accurately predict remaining useful life in order to maximize profits. Many pattern recognition problems involve waveform data, like this walking data. When we have waveforms, we can measure what Dr. Teshima calls variation and abundance. For a feature like a right step, variation is the number of intersections of the waveform, the white dots. Abundance is the duration under the waveform after the intersection, the orange lines. Variation and abundance are treated like gender, weight, and waist size that we used in our body dimension example. Variation and abundance for guitar strumming gives vastly different results than for walking, so differentiating between these two patterns using MTS is not a problem. Here are some areas where MTS pattern recognition has been very successful. Liver disease detection was one of the earliest, analyzing blood test results to decide to order or not order additional tests. Fire detection in hotels. In some countries, guests may be heavy smokers and may cook in rooms with open fires, requiring determination to correctly respond or not respond with firefighters. And automobile collision avoidance. Numerous sensor data will need to be correctly interpreted to decide to take control or not take control away from the driver. Here's some reference and training information about MTS. Dr. Teshima's book is currently viewed as the premier resource. You can also search the web for MTS articles. American Supplier Institute invented the MTS approach and trained me. Here's my email address. You can also request to connect with me on LinkedIn, but please refer to this presentation if you do so.